everyone! In this lecture, we will learn about shift instructions. As the name suggests, shift instructions move binary data in registers or memory units. They support both left shifts, denoted by L from left, and right shifts, denoted by R from right. Shift instructions can operate on 8-bit or 16-bit registers or memory unit numbers. Shift instructions appear to have two operands, with the source operand specifying the number of bits to shift. The destination operand is actually the object to be shifted. So shift instructions are essentially single operand instructions. Data is read from the destination, shifted and written back to the same destination. Therefore, when the destination operand is a memory operand, its word length must be specified. Typically, when using shift instructions, we first move the shift count into the CL register, and then use CL as the source operand. Recall that the CX register is often used for counting. Here, its low byte CL stores the shift count. Here, the CL register is used to store the shift count. However, if the shift count is 1, you can directly use the immediate value 1 as the source operand. Shift instructions are categorized into non-circular shifts and rotations. Let's start with non-circular shifts. Non-circular shift instructions start with S from shift. The instructions are divided into arithmetic shifts and logical shifts, depending on whether the operand is treated as a signed or unsigned number. If the operand is treated as a signed number, arithmetic shifts are used. Arithmetic corresponds to arithmetic, so arithmetic left shift is represented by SAL, and arithmetic right shift is represented by SAR. If the operand is treated as an unsigned number, logical shifts are used. Logic corresponds to logic, so logical left shift is represented by SHL, and logical right shift is represented by SHR. The difference between arithmetic and logical shifts is whether the sign bit remains unchanged. We will explain in detail later. These four instructions have different functions, but they follow the same usage rules. We will use SAL as an example to explain. SAL has two operands. The destination operand can be a register or memory operand. If it's a memory operand, its word length must be specified. The source operand can be 1 or CL. When the shift count is 1, the source operand is the immediate value 1. When the shift count is greater than 1, the source operand is CL. Next, we will look at the specific operations of these four instructions with the help of several diagrams. First, the arithmetic left shift SAL and logical left shift SHL have the same function. They shift data left by 1 bit, moving the highest bit to the CF flag first, then shifting the remaining bits left by 1, and finally filling the lowest bit with 0. Since left shifts cannot preserve the sign bit, arithmetic left shift and logical left shift have identical functions and operations. Now, let's look at arithmetic right shift SAR, which maintains the sign bit as much as possible while shifting right. Therefore, when performing an arithmetic right shift by 1 bit, the lowest bit is moved to the CF flag first. Then the remaining bits are shifted right by 1, and finally, the highest bit is filled with the original sign bit. Finally, let's look at logical right shift SHR, which simply shifts right without considering the sign bit. Thus, the difference between logical right shift and arithmetic right shift is that the sign bit is filled with 0 instead of the original sign bit. In summary, any shift instruction will affect the CF flag, as well as the PF, SF, ZF, and OF flags. Non-circular shift instructions are mainly combined with addition circuits to implement arithmetic operations. For example, non-circular left shifts can assist in implementing multiplication operations. Non-circular right shifts can assist in implementing division operations. Now, let's learn about rotation instructions. The meaning of rotation instructions is to shift data such that the first and last bits are connected, keeping the relative positions of the bits unchanged while changing their absolute positions. For example, for 8-bit data using rotation, all 8 bits remain, and the relative positions between the bits do not change. Only the absolute positions change. Rotation instructions are not denoted by shift, but by round, so the abbreviation in the instructions is R, not S. Rotation instructions are divided into rotations with carry flag CF and rotations without carry flag. Rotations with carry flag mean that CF is also regarded as part of the data and cycles together with the data. Thus, these instructions are represented by RCL rotation with carry left and RCR rotation with carry right. For rotation with carry left and rotation with carry right instructions respectively. Rotations without carry flag mean only the data is cycled, and the value of CF is changed incidentally. These instructions are represented by ROL rotation left and ROR rotation right for rotation without carry left and rotation without carry right instructions respectively. The 4 instructions have slightly different functions, but their usage rules are the same. Let's take the ROL instruction as an example. The ROL instruction is a dual operand instruction. The destination operand can be a register or a memory unit. If it is a memory unit, its word length must be declared. The source operand can be the number of shifts, or 1. When the number of shifts is only 1, the source operand can directly be written as 1. If the number of shifts is greater than 1, the source operand uses CL. Below, we will compare non-rotating shifts and rotating shifts. Non-circular shifts are destructive. Bits are lost during the shift. However, rotating shifts are non-destructive because the bits that make up the data are always preserved. Therefore, after shifting the appropriate number of times, the data can be restored to its original state. This is the biggest difference between non-rotating shifts and rotating shifts. We will now look at the differences between these 4 instructions through 4 diagrams. First, the rotate left with carry and rotate right with carry. As you can see, shifts with carry all consider the CF bit as part of the circular loop. For right shifts, the lowest bit is first moved to CF, then the other bits are shifted right by 1 position. And finally, the original value of CF is moved to the highest bit. For left shifts, the highest bit is first moved to CF, then the other bits are shifted left by 1 position. And finally, the original value of CF is moved to the lowest bit. What about shifting without the carry bit? It means only moving the data content end to end, while modifying the CF value with each shift. For a right shift, the lowest bit is moved to the highest position, and the other bits are shifted right by 1. The shifted out lowest bit is also assigned to CF. For a left shift, the highest bit is moved to the lowest position, and the other bits are shifted left by 1. The shifted out highest bit is also assigned to CF. The rotate instruction only affects the CF and OF flags. Now let's look at applications of rotate operation. Application 1. Testing the status of specific bits. For example, if we want to test whether bit 1 of a data is 0, we can rotate the data to move bit 1 into CF, and then check the state of the CF flag to determine if bit 1 is 0. Application 2. Swapping high and low bit segments of data. For example, for an 8-bit data, performing a rotate left without carry 4 times will swap the positions of the lower 4 bits and the higher 4 bits. Application 3. Combining with non-circular shifts for 32-bit or longer shifts. For example, to implement a 32-bit non-rotate left shift. We can split the data into the lower 16 bits and the higher 16 bits. The lower 16 bits are directly shifted left without rotation, while the higher 16 bits are rotated left. You can verify whether the result obtained this way is correct. That's all for shift instructions. Next lecture, we'll learn about unconditional jump instructions. See you next time.